Module 9.1 is going to be one more section of theory before we reach Module 9.2, where we're going to tie all of this theory that we've been covering across different modules together to look at some business applications. Again, specifically we're going to be looking at optimization problems that primarily relate to the idea of finding absolute extrema. So we've encountered that word extrema before, and the thing to keep in mind is that's just a general term to refer to both maxima and minima, or maximums and minimums. So the difference between absolute and local extrema, which local extrema is what we covered before, is that an absolute maximum or minimum occurs if some function value, f of c, is greater than or equal to f of x, so our function evaluated for any other value of x, then that function value f of c is the absolute maximum. So what we're saying is when we evaluate the function at this point, x equals c, the value of our function at that point has to be larger than our function evaluated anywhere else on its domain. And then similarly, if f of c is less than or equal to f of x for all x, then f of c is the absolute minimum. So if we look at these two functions below, what we have is the curve on the left. We could identify 2 points here, which would be a local maximum and a local minimum. So going back to ideas that we previously introduced with the first derivative test, our function changes from increasing to decreasing. So that gives us a local maximum. And then our function changes from decreasing to increasing, so we have a local minimum. But these aren't absolute maximums because even though we have this local minimum, on this end of the graph, our function is decreasing further and further down to negative infinity. So our function is going to take on smaller values than this point. So a local minimum just means that in this area, this is the smallest function value. So the function might take on a smaller value somewhere else, but in this relative region, that's our smallest value. In this region, that's our largest value. The difference is going to be for this module, what we're looking at are points like this one, which could be classified as an absolute maximum. So it's an absolute maximum because this is the largest value this function ever takes on. As we follow the graph to the left, this is just continuing down to negative infinity. As we trace it to the right, continuing down to negative infinity. So our function is never going to achieve a value above this value of 4. So we can classify that as an absolute maximum. Similarly, if we had a parabola headed in the opposite direction, going up to positive infinity on both ends, then we could classify this point as an absolute minimum. Now each of these points are also a local maximum and a local minimum because our graph is changing directions from increasing to decreasing, from decreasing to increasing. But using this word absolute for the maximum and minimum just makes it a stronger statement, saying that the function is that's its maximum value, not just its largest value in some relative range. So any given function could have local extrema, absolute extrema, it could have neither of those, or it could have both. So with any given function, there's a variety of things that we might uncover or discover. Now let's go back and take a look at that first graph that we were considering before. So this graph on the left that had a local maximum and a local minimum. If instead of considering that graph for all values of x, we restricted it to the interval of -3, 2. And we're considering it on that closed interval. So -3 is included, 2 is included in the domain that we're looking at now. So now this is the curve of our function. So it's the same curve we looked at before, except now our function is ending at each end of that curve. We're not considering this continuing on to infinity anymore. So on this restricted interval, we can now find absolute extrema. So now that we've restricted this function to a limited domain, we can see that we have a local maximum, but now since the graph isn't extending beyond either of these two endpoints, this is also now an absolute maximum. Again, not for the entire domain of the function, just for this restricted domain. And now this endpoint down here is the absolute minimum of this function on this closed interval. And what we can be a little more precise in noting is that one of these extrema happens at a critical value. Again, critical values being wherever our first derivative is equal to 0, so anywhere that we would have a horizontal tangent line. So we have one of those absolute extrema occurring at a critical value, and one occurring at one of the endpoints of that closed interval. So this leads us into a pair of theorems that we can use to identify and classify absolute extrema. The first is the extreme value theorem, which tells us that if a function is continuous on some closed interval from a to b, then it has both an absolute maximum and an absolute minimum on that interval. So any function that we're looking at on some closed interval, as long as it's continuous on that interval, is going to have both an absolute maximum and an absolute minimum. Then we compare this with another theorem that talks about locating those absolute extremes. If absolute extrema exist, they must occur at either critical values, so again, points where we have a horizontal tangent line where the first derivative is equal to 0, or they must occur at endpoints. So anytime we're considering a function on a closed bounded interval from a to b, we know that absolute maximums and minimums are going to occur, and they're going to occur either at critical values or endpoints. And that's going to give us a structure for identifying and classifying absolute extrema.